It's more about my hobby.
Yeah.
I came here because geostatistics is under the mining engineering department in the United States, but in the other side of the world, it's geology. Yeah.
Oh, yeah.
How about you? Important to have.
Yeah, but I don't want to, I don't more on. Because you said like. What? No.
You got all
It's, I don't. For my mommy. No, they do. From the same day you remember, I was so excited. Oh my God.
report like over.
One of the major items. So ocean currents are a really big deal. Um, the tailings management is really critical if we process the ore on board, which we have to, because it doesn't make sense to move all of that material back onshore for processing. We have to do a level of mineral processing on board. So the tailing is an issue. You cannot just dump it back in the ocean and say bye bye. It's going to sink in because it's going to go with the currents. But we have to really go back and place it back in the ocean floor and secure it. But of course, we have to do a lot of environmental monitoring that we have, make sure that nothing, is going to go wrong. But as far as outer space, let's see. Okay. Outer space, both of them, are volunteers. We don't have much of a track record with them. We don't know the geotechnical information or geological information about outer space, and by gosh, even in the deep sea mining, we only have explored less than 5% of the deep sea. We don't really know much about the geology and the geotechnical setting. We don't have operational experiences. It has to be done remotely by robots. So for both cases, we have to do fully automated mining. Lack of access for maintenance. I mean, this is a major issue because you might say that we're going to deploy a robot to do the work, but the robot cannot go forever, right? You need to change the tools, you have to maintain, and of course, access to even parts and supply is a major impediment. Distance for transportation of the material in both cases. Right now, we're in the space mining, we're not thinking about bringing it back to Earth, but we may extract water and bring it to lower Earth orbit, right? And use it. So transport is an issue with this deep sea mining. We have to take material from middle of the ocean, bring it onshore for use. And of course, supply chain issues. If you see back, side by side, these are the challenges we have with the environment. In outer space, you have to deal with vacuum, and we thought that's flat. Deep sea, we have to deal with high pressure. Vacuum is -1 atmosphere, right? Deep sea, we are talking about, we should go to 6,000 meters, which is the record right now that we have explored. That's 600 bar, not -1. Major problem. Radiation, we know for sure on the moon we have radiation in outer space. We don't know what's going on in the deep sea. Temperature, of course, for moon mining, we are going from -180 to +120, 300 degrees Celsius differential. In the bottom of the sea, the typical temperature is about 4 or 5 degrees Celsius, right, deep sea. But as we get closer to these volcanic spots, then you have a huge differential temperature in the water. Low gravity is an issue on the moon, but in the sea we have the buoyancy issue. Again, some sort of weightlessness. Potential for impact by meteorites on the moon, but you don't have that in the ocean, but you have to deal with the ocean current instead. Dust suppression is a major issue on the moon because the dust that gets floated in the atmosphere, there's no atmosphere, gets up there. It has a tendency to stay up for a while. In deep sea, we have the same issue. To get the dust into the water, tends to stay. Limited source of power, an issue on the moon, an issue in the bottom of the ocean. Difficulty in repair and maintenance, same way. Cost of material going from here to the moon. Okay, we may not have that, but cost of operation in subsea is also substantial. And of course, on the moon, the problem is no humidity. Nevertheless, we have the issue of active volcanoes on the ocean. This is proposed actually by.
Just click in this slide.
It's not responding, so it's probably not my system.
This one.
Hi.
It's up there. Up there. Up.
No, it's that. Okay. However, one thing that is also negative about working in deep sea is the issue of environment. Because on the moon, we don't know of any living organism, at least till now. Nothing has been recognized. But bottom of the sea, my gosh, there are other living organisms. But the environment is very, very sensitive. All right, what does it mean when we are doing operational planning? Of course, it means that you should use fully automated system. You have to have a lot of sensory system to actually tell us where we are. And real time is going to be problematic. From the moon to Earth, we have a delay, time lag between the signals. Bottom of the sea to the surface, we may have that same issue, unless we are hardwired. We have to have a very agile system, which is very flexible. Limited amount of force available to cut the rock on the moon. We have the same issue in the bottom of the sea. Limited power and also transport capacity. And of course, when you're excavating, breaking rock, it takes the same amount of force to break the rock with a certain bit that it takes onshore, on the moon, anywhere. So if you have a rock that's at 100 megapascal and you want to break it with a pick or a disc cutter, it doesn't matter where you are in the universe, it takes the same amount of force. Problem is that you don't have that force available on its operations. So these are the space-related pictures. Again, taking samples and then excavation. On the fluffiest stuff on the surface of the moon, we are okay. But when we get to harder stuff that's underneath, we have to excavate. This was actually a system proposed way back about 2006 to actually use something like a surface milling machine to dig up the surface of the moon, similar machine. But the problem there was that for different type of material, you need to use different type of color heads. Great, we have it here. You can switch up, switch over a color head and do something else for different cutting scenarios. You can't do that on the moon. You can't do that in the ocean. So back there, when we were studying this, we developed a system that could actually expand or contract relative to the material that we were cutting. This was proposed for the moon, made a full-scale test, prove the concept, works fine, right? However, again, this is one of our current projects. We are developing a robot that can actually excavate the surface of the moon and fill the depressions, move the rock samples, compact it, and make a round 10-meter diameter landing pad. This is an ongoing project. We're working on it mines. A lot of this is going to have be also used for deep sea mining because there's certain similar environmental setting. The issue of force that I mentioned earlier is going to pop up here. Here, what you see is that if you have a machine that wants to excavate some sort of a material, on the moon, if you want to apply a ton of force to break the rock, the mass of the machine has to be over 20 tons, right? Is that a problem? It's a huge problem. Getting a 20-ton machine on the moon is going to be billions of dollars in cost, right? So we had to come up with some sort of an alternative to, brace the machine down or come up with some sort of a counteracting force. So this is NASA's response to that issue. If you don't have a mass to apply a certain load, this system is called RASER, has two counter-rotating drums that can actually rotate with the forces are balanced, and you can fill up the drums with material and then lift the drums and drive over the surface. What can we learn from this in ocean mining? You can pretty much use the same system, counter-rotating drum, to cut the rock and then set it up. So this is again a close-up of view of the drum. Okay, so let's look at some of these challenges and see where we're at. The technology of deep sea mining has actually been broken into several different components. You have the surface facilities and equipment, which is the vessel. You have the transport system, intermediate. You have the subsea sections, and then you have the excavators or, the units that are working around. These are the sections that are shown in the graph. The transport is primarily the hydraulic, right? And then you have these sea floor units that are supposed to do the excavation. And what I'm going to focus on are the cutting and excavation subsystems. So these are the pictures from the Nautilus. These are the pictures that were taken in the period around 2004 to 2009. Again, you can see the rocks and some of the samples that have been knocked out and removed, brought to surface. Again, these are the sampling and coring system. Looking at the surface, imagine something like the skull quickly solidifying its photostatic consistency. In the coring, and this is the unit that Nautilus used at the time for their exploration. Again, you can see some of the pictures and drawings of the units, essentially deploying the subsurface units here, back into the ship. This is how it looks like going down. And if we look at the details, you realize that in the excavation unit here, they have a couple of counter-rotating drums that could actually engage the rock and break it up. And then as it breaks the rock up, there is a sort of a pipe right behind it with the flow that is going to suck up the material and push it up. Subsequent to the initial designs, they actually did some trials. I mean, these are the units that have been actually tried to do different type of mining. And they have been essentially deployed on site. You can see these are the ones that actually can pick up the nodules. There are some other machines that can actually break rock. These are the units that again have been tried. We have similar machine to this for coal or trench mining on surface. But as you can imagine, the reaction forces to a unit like this is going to be pretty heavy. Therefore, I don't know how far they can go with it. This is another unit with a road header type header head, double drum. But again, there is no counteracting effect here. So the reacting forces are going to be fairly difficult to deal with. One of the major challenges in space mining, also deep sea mining, is positioning. On surface, we have GPS, right? Essentially locate your equipment. Underground, we have that problem because GPS doesn't work enough, right? On the moon, we have the same problem because there is no set up GPS system to locate your equipment. You have the same issues down at the bottom of the sea. So there are quite a few systems that are being proposed to essentially locate the equipment because you need to know where your equipment is before you can actually start mining, right? And if you do the exploration and know where the high grades are, you're supposed to be in the high grade area. Essentially, the issue of locating the equipment. There are two systems that are now proposed and being used, beam echo sounders and also the laser-induced breakdown and spectroscopy. So both of them are something similar to what we are doing actually in underground mining, by developing point cloud, scanning the environment, scanning the surfaces, creating a point cloud, and then augmenting the point cloud. So that's what they're using, or proposing to use in deep sea mining. There has been some experiments with a unit called Apollo 2. This is the nodule collector. They've deployed this unit, and as you can see, the testing that was done in the Atlantic Ocean tried to track the plume and the dust that is actually getting into the environment and try to keep track of it to see how far it goes, how they can actually contain it. There has been quite a bit of work on this topic past few years. One thing that came up during the conference that was really neat, I don't know whether it's been practical, but hopefully it would come through. There's a company called Impossible Mining. They have proposed this type of robot. The difference here is that it's not raising the floor to pick up everything, right? It's hovering over the seafloor and using its sensor system, visual, LiDAR, whatever. They're using the sensor system to locate the nodules in the seafloor. Also using AI to identify if there is any living organism on the nodules, right? And then if they identify the nodule with the least amount of living organism, an arm will extend and pick that up. So you're not really breaking through the floor, you're picking up pieces so that you have the least impact on the environment. The system doesn't have a track or wheels, so it's not going to stir up the floor, right? So it's going to hover over the surface to pick up nodules. What they anticipate here is that it would have the least impact on essentially the environment because it's not puffing all this dust around. So with the flow, with the current, and it's not removing all the nodules, leaving some of them on the floor to essentially allow the living organisms to continue as they do. From mining and environmental point of view, brilliant, right? Whether or not they're gonna make it and make it operational, yet to be seen. But this came up and I was pretty impressed with the whole concept. So we have to actually minimize our operational risks, right? We have to develop a system that is fairly efficient, essentially minimize the use of energy. Therefore, it uses the lowest amount of energy, highest resilience, because it requires least maintenance, and essentially try to reduce the amount of maintenance. What this means is that we need to actually characterize the rock that we're going to be cutting down there. Nodules are one issue, but we need to excavate the rock. ABC, the first step in rock excavation is to understand what is it that you're cutting, and then use the proper cutting tools for it. At this stage, our knowledge is really limited, and the material is really valuable. So it makes it very difficult to really make a decision about the cutting system. Strength is very critical for us because it determines what type of tool to use. Abrasivity is another issue. We don't know much about the abrasivity of the material. Abrasivity is critical because it determines the tool life. The more abrasive the rock, the faster the tools will wear out, the more frequent the maintenance requirements is. And again, we discussed that we can do maintenance on a regular basis. Imagine just lifting one of these units up to the surface to do maintenance is going to take not hours, it take days. There's a lot of these high, highly automated systems that are supposed to go to the depth of thousands of meters, right? Their sensor system, the entire system is so sensitive that if you lift them up in a short period of time, it could actually malfunction. Okay. So the issue is that for now, our bread and butter at EMI has been that we need samples to actually conduct this swab test to minimize the risk, right? When you cut a piece of rock full scale with the tool of your choice, you're removing the risk, you're actually eliminating the risk of what's going to happen there. But we don't have that luxury right now. Now, of course, if we could estimate the forces, then we can actually use computer models to see how the whole unit of the whole machine is going to work. But again, full-scale testing is missing right now. And of course, there are certain models that can estimate the forces and therefore could be used in computer modeling to estimate the production, but this is only for the feasibility. Definitely not recommending it for the actual operational unit. Again, looking at these machines that have been tested before, again, this is like a dredge cutter head that we use for cutting phosphates and low-grade sandstone in channels. The next machine is a trencher, and the third one on the right is like a transfer flow header. None of these machines are, from the operational point of view, are new, but we have never used them in this environment. Okay, so the next few slides are about the excavation. When we talk about excavation and drilling, there are different forms of tools that we use. For drilling, these are the units, PVC bits or button bits for harder material. For excavation, we use radial tools or pick cutters for very low strength rock, non-abrasive, medium strength rock, partially abrasive, and then the roller type cutters to use for different type of hard and abrasive rocks. Now, what we know from the past experience on the samples that were retrieved from west coast of Australia. These are the measured strength values, typically not very high. Right, density for again tensile, not really high. Point load index, right? Unconfined compressive strength, average megapascal, right? This is really easy to track with Pickle. You're okay there. However, there were also some measurements that ended up to be very high. And as far as Sorshar, right? There are some Sorshar values that are high, meaning that the rock is abrasive. That is going to be problematic. So from the strength point of view, you might be able to actually operate the pick cutters on not all, but the majority of the rocks. But from abrasivity point of view, you're in a bind. Because this means that the machine needs a lot of inspection tools and intervention. There were some of the formations where the UCS reached up to, 190 megapascals. That's definitely a problem, right? 190 megapascal means that you have to go back to the roller cutter, disc cutter, or bottom bits. The problem with disc cutter and bottom bits is that by the time you put a few of disc cutter on a machine, that machine is going to be really, really massive. Pick cutters, you put 40, 50 L on a cutter head, you're good. Roller cutters, not so much. Needs a lot of force, requires a massive machine. So if we run into these type of formations there with high Sorshar values of 3 Sorshar scale is relatively high, right? It is low grade granite, high grade, or very highly abrasive sandstone. And we know that the pick cutters touch this damn material, boom, it's gone, right? So if you have then a mixture of these rocks, in order to be safe and maintenance free, you have to go to the roller, these type of tools, right? Like a machine like mobile miner with the roller, the disc cutter. Look at the mass of that machine. It's huge, right? The machines that I showed you here are 300 ton plus, and 300 ton plus onshore, which means that you get the full benefit of the weight. Down below, you don't have that 300 ton, close to 250, right? So if we were to use machines like rotator with the pick cutters, again, in softer material, it's doable, right? Like the machines that we saw earlier, that Nautilus has tried. But if in the mix they run into that 190 megapascal material with high abrasivity, in a matter of minutes, you wipe out all the heat on the machine. So the machine is going to be dysfunctional. There are certain type of machines in use right now, like in this case is a shaft sinking machine that uses that type of drum to excavate. So there is a possibility that you may consider setting up a shaft sinking operation on the surface so that you have some sort of a confinement to grip onto the walls and go down. So that's a possibility. But again, if this machine runs into those hard rocks, the teeth on the cutter head is going to be wiped out. These are some of the schemes of the shaft sinking systems with rotator cutting edge that are being used. And again, double drum machine for counteracting.
Yep.
What does blind shaft mean? Is it the same thing as like blind stove?
No.
Okay.
Blind shaft means that you excavate and you go downward.
Yeah.
Right.
Okay.
But when you say a stove you typically need to have several
Yeah.
axes and in and out and so on. But blind shaft is blind. It's an excavation goes,
Okay.
Vertically down. Also in this line of thinking of what we can do to mine the ocean floor, a company called Bauer has come up with this type of system. A tripod that's with sink to the bottom of the ocean, grab onto it, and then start mining down. Oh, okay. Okay. I'll go to the questions in just a couple of minutes, so we have a little bit of time, I'll take care of that. Okay, so their system again, is based on what they do on shore with the, machine hydroplane. Look at this machine. The concept is double drum. And the whole thing is about counteracting the forces, right? So they're trying to, integrate one of these hydrophraise units that are used on shore for slurry walls in construction, build it into a much larger unit, send it to the bottom of the ocean, and let it cut curve its profile down below. Right behind the cutter head, there is this intake for lifting of the material. So it's essentially sucked up the cutting into the crossing unit. So this is what is used on surface onshore for slurry walls with hydrophraise machines. They're trying to use the same concept in the bottom of the ocean, and you can imagine the unit is going to be pretty massive. So it's better to do some testing of the rock at scale to know how the rock is going to be cut and what it entails. And of course, there are a lot of available information about bit life. We have to combine all of it to be able to actually deal with potential threats. Of course, one of the new development in the past couple of decades is the PVC, so it can actually be extended life. You cannot use this onshore in dry conditions because the heat that the bit generates is gonna actually go above 400 or 500 degrees Celsius, and diamond turns into graphite. It's not gonna work onshore, but offshore, it works because you're underwater. Okay, couple of things that we added to this discussion was that we are working on the concept of a smart bit that can measure force. The use of it for deep sea mining is that it allows you to monitor your bit health to see if the bit is sharp or not. And these are some of the slides of this unit and the testing that we have done to actually prove that it can detect each way, right? And we have proven that we can do that and also identify the formation. So deep sea mining is going to happen when we need to excavate rock. You have to essentially develop new systems. And what I try to do is to give you a glimpse of what the challenges are. As far as positioning the unit, the ability to be able to break the rock and efficiently ship it to the surface. And also what it takes to really maintain an excavation operation on a sustainable basis and what the challenges are. I'm going to stop here and take questions here. And of course, there was a question in the chat that I'm going to address. Can you provide information on deep sea mining project cases studies that have overcome this challenge efficiently? Okay. Now, Natalus was the only commercial, deep sea mining. It got a license to work in west coast of Australia, operated a couple of years, but wasn't very successful. Was bought out by Rio or one of these big, right? Rio Tinto bought them out, and they're not really operating right now. So as of now, there is no real deep sea mining operation anywhere in the world. As I mentioned, the one that's coming up pretty soon are the Norwegians in the northeast of Scotland, that continental rift, and they're going after manganese nodules, not hard rock cutting. Okay, question?
Yeah.
Comments?
Well, you know Chris Wyatt, right?
Yeah.
So Chris, they've been going out looking for 2 UK companies. They have a concession in the Pacific diesel water.
Okay.
And they're extracting currently batch processes out of their concession for, going through the process, and it's equipment perfection. One thing that Chris and Bob Cameron are working on
Okay.
for the UK government is coming up with a process for coming up with, compliant resource estimates, which are required for financing.
Right.
It's interesting, that Chris and Bob are indicating that more than 60% of the nodules, at least in the Pacific, are subsurface. You can't see them.
Yeah, okay.
So it's an interesting problem. I got a bunch of nodules upstairs.
Okay.
It's interesting.
It is, thanks. It looks like that there are some activities going on, but still, to the point that I could actually dig in, there is no ongoing major operations. Commercial, right, yeah. You're right, they're probably batch processing to see if they can actually make it sustainable, right, production.
Yeah, the topic is really interesting, but my question is, that the solar system is fully controlled by items like the gravity of Earth, gravity of the Moon, gravity of the planets. So mining all this, like mining the Moon or mining the Mars, for example, would it affect our planet? Or we talking the heights?
No, the amount of mining we are going to do is not going to affect the gravitational, condition of the planet. I mean, look, we have been mining on Earth for what, thousands of years, and nothing has happened as far as gravitation. Best of the environment here and there, but nothing to the gravitational pull in the galactic scale. The issue on the Moon, of course, as I said, we don't know of any living organisms, right? So at this stage, there is not much of an environmental concern per se, but operational. Now, and you can see that there is quite a bit of a race going on in the US, India, China, Russia to get there and try to stake in the ground and say it's fine. Question?
Yeah, this topic is right now spicy already for environmental for deep sea mining. I will turn even worse when we start talking about doing this in international waters because no one wants to take care of it.
Yeah.
But I am a little more curious about the operational aspect of these machines. How exactly, I believe that you heard about this in the conference, is the lubricant system in these machines given the pressure and given the seawater?
Correct. You're right. The lubricants are an issue. My guess is that we have looked at this in the context of moon mining. We decided to go with the solid lubricants, graphite, so that you can avoid some of the issues. But I don't think it's resolved completely. It's not to the extent that I'm seeing. For Moon and Mars, for space mining, the issue is the change in temperature. Minus 150 plus 150 degrees Celsius kind of mess up everything, right? If you have any fluid, it's going to freeze up. But in the bottom of the ocean, if you're dealing with 4 degrees Celsius, really not a big deal. The pressure is the main issue. And if we're dealing with pressure, the main problem is the seal, not necessarily the fluid itself in the system. The seals are going to be very difficult to manage.
I'm the same with definitely the seal is also playing a role to prevent the lubricant being washed out, right?
Yeah.
Okay, question from
Mohammed.
So, actually, my question is basic, what we are referring to the deep sea mining, like what is the depth we are talking about, and if there is any trial, what was the depth in that sense?
Good question. Of course, well, when we say offshore, anything in the water is offshore, right? When we say deep sea, based on, it's not a standard, but we're talking about 300 to 400 meters and beyond deeper. And offshore platforms in petroleum, they have reached, I've seen as deep as 1 mile, which is 1,500 meters roughly. And the ongoing plans for the Norwegians in the area that you mentioned, they're talking about 400 to 500 meters. Apparently, a lot of these nodules are in that level, 400 to 500 meters, because it's not very difficult and complex to explore, right? So they're doing that. The deepest I've heard that they have sent a vessel with exploration and sensory system was 6,000 meters. So that's the deepest. Of course, you know that in both Atlantic and Pacific Oceans, we have points going to about 11 kilometers, but they haven't explored anything.
Yeah, question, Commissioner?
There's a question up front here.
Yes,
Yeah.
great presentation. I'm equally excited about the concept of having that equipment move around and taking
Right.
appropriate nodules. And my suspicion is that some nodules may be of better grade than
Correct.
others. So, beyond your concerns, I'm also trying to see if you make minds with me on this, that assuming some nodules that are with higher grades have ecosystem
Yeah,
around them, the machine is going to ignore them and go to different, because the only thing is a living thing around it. So
right.
it will ignore those that with higher grade and perhaps go and pick some that are not with higher grade because the ecosystem is absent. And in that case, I'm wondering if the economics will not be economically viable, or it will be disadvantaged somewhere along the line.
You're right. I mean, yes, there should be a balance between all grade, right, versus the living organisms. That has to do with the software part of it, I would say, right? Because your sensor system, you have to develop the sensor system to identify the minerals, maybe based on weight, based on whatever sensor system that you put on. And then once you realize that this nodule is better for a ore, and you have to weigh out your option versus one next to it. That has to do with the programming of your AI system, because it's going to be artificial intelligence looking at it and say, I'll pick this one, that one. I think it's an open question, right? Bottom line is that they have to engage environmentalists and biologists to see if I pick up a nodule that's high grade but with a lot of living organism versus the next one that is lower grade but less living organisms, is that going to impact the ecosystem as a whole? Right? But the concept of picking these nodules up instead of raking through the whole thing, at least is a lot better than, right, one versus the other, right? But selecting between the nodules is an open question.
So thank you for this great explanation about the whole idea. According to Dr. Hughes, he said that 60% maybe of the nodules are subsurface in the sea, deep sea. So is there any operations that from where they enter from the ground, underground going, unless they reach to the sub-sea bottom and then mine from there and coming back and interacting with the water? So
I haven't seen it. I'm not saying it's not.
That is my United
Right.
potential.
Was that?
It's the potential.
Oh.
United Kingdom. And they're digging from the surface and going through the.
Right. Oh, that's completely different. You're talking about Bowlby mine. Yeah, Bowlby mine in Europe. You actually work on that mine. That is a potash seam that goes under the sea and they mine it. There are coal mines, there are potash mines and salt mines that have the same problem. What Fatih is talking about is that right now we talked about raking the surface, the sort of unconsolidated deposit to look for nodules, whereas 60% of them are below surface, we cannot see it. But there is still going to be mined from the surface, right? That volume mine is completely different. Actually, subsea mining is seen that has barrier and fairly high depth. This thing, I haven't seen anybody working on it right now. The discussion is that do we go into a section and go deep and take all the material out? Or we go large area instead to recover what we want, right? That, I think it requires a feasibility study to see which one is better, or from an environmental point of view. Focus on a certain area and go deeper is better, but then you have to dig up, right? So maybe you can develop a small pit, some sort of a, limited area. Right now, the idea seems to be like you're going to cover a large area, pick up other areas on the surface. Right. Any other questions? All right.
Yeah.
Okay. So, we're good.